So can everyone see? Okay. So please a grand round of applause for Andrew Sandberg, and then we get started.
Thank you so much for inviting me over here. I'm delighted to be here. It's been ages since I was in Lausanne and at the EPFL since last time. And I'm one of those people who can't keep to one topic. I gave my dear, poor professor gray hairs because I was supposed to do computational neuroscience. And why did I also do that ethics stuff? And those medical engineering courses and that virtual reality and all of that. So for my sins, I ended up in the philosophy department where I'm allowed to actually work on almost anything. And if there is a running thread in my research interest, it's kind of trying to think about the long run future. Partially, this is because I grew up in Sweden in the 1970s and it was a very boring place. So I read all the local science fiction in the local branch library, and then I decided I want to make that real. I want to make these fantastic possibilities that are so much more interesting than grey Sweden. So I started reading the science part of the library. And then I ran out of science books there, so I went to the municipal library and then the city library and then the university library, and now I'm in Oxford. And basically, I've always been interested in trying to figure out things about the future, both what shape might it take if we don't do anything, but also what can we do to shape it? Are there meaningful ways of shaping the future? And this also leads to the current enormous project I'm doing, which is a little bit excessive, I found out. But basically, I call it grand future. I stole the term from Toby Ord, who coined it. And the question here is, how much future can we get in terms of time, in terms of wealth, in terms of well-being, survival, computation, or other good things? And are there ways of analyzing it? Because it might turn out that some of these things we actually cannot quantify in a useful way. So I'm trying to rigorously find ways of analyzing this, including figuring out what I cannot analyze and trying to put up a bit of a roadmap on that. So I'm writing this ridiculously large book on it. When I presented about this at the EIG in Oxford, I actually had a printout of a book manuscript, and it weighs about 4 kilograms. It's about this thick. It's grown a little bit since then. And what I'm really interested in doing here is trying to compile what we know, because a lot of that manuscript is not my original research. It's actually coming from a lot of different areas. But then I'm trying to put it together and get some sense of how big is the future? And that is a really interesting question. How do we even measure bigness? Grand gives you a sort of feeling that something is good or big or old or something, but it also slightly diffuse, which I think is a useful term because we need to start being precise about what we're analyzing. I'm in the philosophy department, as you can hear. But usually when you start analyzing something, you can't be precise. You shouldn't be too precise because you need to figure out what's going on in the field. And later you can start actually figuring out what measures are interesting. And there are things like how far can we go? How long distances can we travel in space? There are interesting questions like how many people could there be? How much moral good could there be? Well, that's an interesting question because moral good, how do we even measure that? But there are also interesting questions in this domain, like are we early or are we late in the history of things? And we might want to use that to think about what is there to hope for. If we are very late in history, maybe the last remaining chapters of history, that's everything we can affect. And there maybe isn't that much to hope for, but we better make that count. So we get a happy ending for humanity or the universe. Or it might be that we're super early, in which case we might have a responsibility for an enormous range of things. But on the other hand, we might have very little understanding of what's going on because we have not yet figured out many of the more important things. Another interesting thing that immediately comes up when I start talking like this, there's some critically minded people among you who already start thinking, wait a minute, Anders is always about more. There's a very optimizing mindset here. And you could validly criticize that and say trying to optimize everything is dangerous. Certainly, we have found that when it comes to artificial intelligence programs that try to maximize something, do have some untoward side effects. And you could argue that trying to optimize your life can quite often lead to bad side effects. Sometimes it's much better to satisfy, make something good enough and be happy about it. And there are some philosophers saying, no, you shouldn't be breaching certain moral duties or boundaries, but anything below that is totally fine. But on the other hand, we also want more justice. I don't think anybody would say, yeah, we can satisfy justice. We got about the right amount of justice in the world right now. We don't really need to care too much about the other injustices. We already produced enough justice. That seems to be a totally absurd position. We should be striving for more justice. Anything else would be crazy. Similarly, we definitely might want more insight and more wisdom. Again, some of the work here might be done by that wisdom is almost defined to be good insights that make your ability to choose what's right better. So by definition, we should always want more wisdom. We might be careful about wanting other things that not inherently making things better. But this is kind of further down the line. I'm going to start out with the simple part, because the philosophical parts are debatable and complicated. I'm interested in stuff I can think about well. And I'm originally trained as a computer scientist who later branched off into a lot of other disciplines. But I'm very happy when I can measure things, when I can get numbers out of it, rather than having to do a 10-page philosophical argument. And this actually began at another effective altruism meeting in Oxford many years back. I think it was somewhere around 2015, where I was thinking about how many future people there could be. And I tried this metaphor that if a human life is like a very fine dust grain, then the total human population today, at least back then, when it was about 7.1 billion, you could fit in kind of in a pile of dust in my hands. Now it's a bit bigger pile, and there would be entire nations leaking through my fingers. That's all human lives today. What about all human lives that there ever been? Well, that would be about a big rucksack, which would also be spilling entire empires at the seams. That's kind of a cool metaphor, showing the number of human lives and that we have a lot of past lives. And then you can start thinking about how many future human lives there are. And it turns out that this works well for the more modest possible futures. Because there I can start talking about the futures where there is a big dune of dust here up on stage or entirely filling this room, or a dune of dust the size of a Great Pyramid of Giza. But some of the scenarios I'm going to talk about, you end up with enormous numbers of future lives so big that we need to start using astronomical comparisons. Human lives like the rings of Saturn, which is beautiful, except that none of us have a good sense of how much mass that is. And it turns out that many of these metaphors break down. But that is interesting too, because this is also a little bit of an exercise about what can we think well about. So let's go back in history a bit. So generally, humans really like thinking about the future. A lot of that is just what we call practical intelligence. When we wake up and go out of our cage in the morning, we try to figure out a prediction about where can I get water, where can I get food. And those predictions are quite important for getting water and food. And actually, all our ancestors were pretty successful in achieving them. But we have a general intelligence. It's not just that we think about where I can get water and food today. I can realize that winter is coming. I'm going to save some water and food. I can envision that after winter there are going to be other periods of time, or that the winter might be unusually harsh. I need to save more food. This kind of planning ahead and envisioning things that are not present right now, but could be present or are likely to be present, or I could make to be present by doing something. That is, of course, part of the reason we humans are so successful on this planet. It's not the only one. I think our ability to communicate is another really important thing, because I can tell you my idea about the winter this year might be really bad. We should save extra food. And you might agree or not agree. We might form a joint intention as a tribe that, yeah, we're going to save extra food because Anders might know something about the weather. Otherwise, we're going to blame him when it's a mild winter. These group intentions are super effective. And together with a bit of intelligence, a bit of group intention, a bit of cumulative culture, because we can tell stories about harsh winters and what you need to do about them, or how the one trick to survive a harsh winter that then is a tradition in our tribe long after any of the individuals that came up with this trick are gone. These are things that mean that humans have taken over the planet. But you can, of course, generalize this mode of thinking to other things that are beyond what we normally think about. And indeed, it turns out that all human cultures are very interested in the future, not normally in a predictive way. Most cultures have what we call an ecological time, that is saving up for winter, thinking about the routines of life. And then you have a structural time surrounding it, history, our traditions, our ideas. Outside that, there is the hand-wavy mythical time that kind of tell really good stories and give a meaning about what the universe is about. And that is found in practically all cultures. And making predictions about the future, there are the practical predictions that are very different from the predictions we often do about the more structural stuff, because that is more organization. It's rarely that you care about the tribal shaman being right or wrong. But what happens, interestingly enough, when we get towards the more modern world, is that the structural time starts getting extra structure. We start with chronology. We start measuring years, not by who was ruling the kingdom, but actually starting at some year zero and working forward. And if you have a number for your year, you can imagine that going on absolutely forever. When the Seleucid dynasty introduced this kind of numbering, there was rebellion in some part of the empire because people realized this is chronological warfare. They're totally wiping out our idea about how time and history is supposed to work. Now, the really interesting thing happens when you get the scientific revolution starting to happen, because then people started to realize, wait a minute, the rocks are actually giving evidence about the world being really, really old. Not just older than our history, but older than humanity. There is deep time here. And this is time that doesn't deal with human dramas. Normal, mythical, and structural time is all about history and our gods. But what the rocks are telling is that there was endless ages where there were no humans around, and that the world was doing things and things were happening. And this was an enormous shock to many people during the 1700s. Then, of course, there was also the realization that, we seem to be a species. We have seen other species go extinct according to the fossil records. We might be next. Oh, that took a long while to actually get into people's mindset. Thomas Moynihan has written a really good book about the history of existential risk, where he points out that for long after this was realized, many people were not taking it as a serious problem because they would imagine other humanities would show up. And besides, there are probably humans on all the other planets. Basically, the starting position for many people was that every place that can have minds probably has minds. And in that case, well, if we go extinct, that's sad, but it's not the end of everybody's world. It's only in the 20th century when we realize that much of the universe is actually very inhospitable and we are only in a very small part of it where existential risk really started to bite. But going back to the 1800s, people realized that the universe actually can throw stuff at Earth. There might be comets hitting Earth. The sun is changing. Earth might not remain inhabitable forever. And these are extrapolations forward of what astronomers had been becoming better and better at deducing backward. Basically, as astronomy figured out the history of the universe, it also hinted that this might continue. So in the 1960s, Martin Rees coined the term physical eschatology for using our models about what's going on in the universe to extrapolate its future. Eschatology is a word used in theology for the end of the world, the meaning of it all. Basically, all the stuff that you find in the revelation of St. John in Christianity, the end times. And he pointed out somewhat jokingly that we maybe call this cosmological study of collapsing universes physical eschatology, which is actually a pretty good term. We can use what we know about the past to infer some things about the future. And one of the interesting things that happens when you have a scientific view is, of course, the more deep past you see, the more you should expect a deep future. Not just a deep future of the cosmos, but a deep future of geology, a deep future of biology, and a deep future of humanity. if there have been hundreds of thousands of years of humans around, at least we should expect maybe hundreds of thousands of years of humans in the future, at least if we survive. Now, that doesn't necessarily mean we're good at thinking about the future. People have a lot of ways of thinking about the future. After all, having a futurist give a talk at your company is a common form of entertainment for your personnel. They come in, they say some cool stuff. Moore's law is probably one part of it. They say something about augmented reality or social trends, and everybody feel like we have now gained foresight. We are a very insightful company, and you don't change very much. Of course, if a futurist actually told them your business is crap, it's going to be out of business in 5 years' time, leave a company or change what the company is about, they don't get invited and they don't get paid. But there is a lot of forecasting a future that is basically entertainment. But if you actually care about making a better forecast, there are some domains where you can make decent forecasts and some where you cannot. For example, that map of solar eclipses in the later part of the century, that one is given. We know how the laws of mechanics work on the moon and the sun. We can forecast this with an extremely high precision. Indeed, there are forecasts going thousands of years into the future for where the solar eclipses are going to be. Beyond that point, we get uncertain because we're a little bit uncertain about how the Earth's rotation changes over time. Basically, it depends a bit on how wide the atmosphere is, which depends on solar activity, and some of the rock motion in the Earth's mantle, which changes the inertial moment, so it speeds up or slows down a little bit. There's also a little bit of tricky tidal interaction with the moon. So that means that a few thousand years in the future, you're going to be off, basically going to have a right pattern, but it's going to be off by a number of degrees. So beyond about, I think, 7,000 years, it's going to be about 50 degrees off, at which point it's kind of hopeless. But this is a very well-behaved system. And similarly, the solar system, we can predict the orbits of planets very far in advance. Some aspects of that are chaotic, just like the weather system. There are some orbits that are interfering with each other. So over long spans of time, it becomes unpredictable roughly where a planet is. And we certainly know that with the weather. There is a natural limit on how far you can do forecasting, given a certain amount of information. As you extrapolate it into the future, your uncertainties grow exponentially, and beyond a few months, depends a little bit on scale, you have no idea. Climate is much better because now you're not interested in whether it's going to rain in 100 years, but rather how much is it going to rain on average, and you can make better models like that. But generally, weather forecasting has an upper limit, although right now it's still rather strongly set by the amount of data we can get, and to some extent the computing power. So here we also have advantage. We understand what kind of uncertainty we get. But then you have things like fashion. It's always fun to look into magazines envisioning the fashion of the future, and you get to see all stuff that is looking awfully retro. And the problem is you cannot forecast fashion at all because it's literally anti-predictable. If you could forecast that by 2023, green is going to be the fashionable color, that would mean that it would be very cool not to make a green dress. You would make money in the Paris fashion show by doing something daring that wasn't green. You want to be different. Not too different. It needs to be a decent thing that people are willing to pay money for, but it needs to be different. Same thing in the financial market. If you can predict a pattern in the stock market, you can make money from that. That means that the market dynamics is going to reduce that pattern because people are going to pile on and try to make money from it. So that pattern disappears. So at least in theory, it's anti-predictable. Then, of course, you have various forms of inside trading and other facts that make it slightly more complicated than just that. But there are some systems where we really, really cannot do good prediction, in particular when humans are directly involved, because a lot of our behavior is based on ideas that you cannot predict beforehand. And it's also based on us trying to game the system, either the outside world or other people, and that means that we generate a lot of randomness. The weather is not like that. That's just mainly chaotic, and the planets are kind of nicely well behaved. So what can we do about it? This is something I can go on quite long about, but there is a lot of interesting things to be said about forecasting, but I should probably jump ahead a little bit. Now, one way of doing it is to think about exploratory engineering. So this is a term I borrowed from a friend and colleague, Eric Drexler, and he noted that there are many things we can say about many possible technologies that we know can work because they exist, the blue area. And then there are many technologies and systems we can be pretty certain cannot exist because they break fairly well understood laws of physics. If your computer requires signals to move faster than the speed of light, it's probably not a good and workable design. If the computer is so heavy that it's going to implode into a black hole, it's not going to be a workable computer. At least the gravitational time dilation is going to slow it down. So there are domains that are also forbidden. And then there is a big gap between. And this is where exploratory engineering is a way of examining it. So we can say that if we do it, or we find life on Earth doing it, then it actually is something that is doable. Now, that life assumption is interesting because it's much more of an assumption than if we can already do it. We know to make computers and cuckoo clocks and pumps. We don't know how to make artificial intelligence yet, but we kind of know that natural intelligence exists. So there exist at least some systems, about 1.4 liters in volume, that can do intelligent processing. We know that self-replicating systems exist. That means that there might be other systems we can make. And so far, we've been pretty successful at that, saying, oh, humans will never be able to make something more efficient than a leaf on a plant. That's not true. Actually, we're easily making better energy collectors than photosynthesis these days. It's just that we're not self-replicating, which would be a rather nifty way of doing it. So this is historically a good guess, but it's still a guess. Another interesting thing is that we can automate the tasks we're doing. So if I built a machine by a certain set of operations with my hand, we can imagine a machine doing the same operations. Might be too expensive to use, but once you get down the price, typically it gets much more effective because typically if you automate something, it gets orders of magnitude more effective than humans. And that, of course, leads to other interesting things, including that we can build machines using machines. And one of the interesting results of this line of reasoning is that scale might not be a barrier. So our ancestors that were thinking about the future, they might imagine finding better caves. But we're making caves. They could have imagined maybe hollowing out a good cave a little bit more. We're pouring literal liquid rock and making caves to whatever size. And our more recent ancestors in the ancient world, they might imagine houses, but they could say, yeah, but you can't make a house with 10 stories. That can't hold together. And they were partially right. They didn't know how to do that. And they didn't have the resources to put together enough stone to make it. We found ways of automating that. So now we're regularly building very large buildings. And in principle, if we wanted to build much bigger houses, we could. It's just that there is an economy of scale that stops after a while. Eventually, the skyscrapers get rather silly, and you get the real problems getting the plumbing to work, and most of the interior is elevator shafts, etc., etc. But one of the interesting things is that when you realize that scale isn't the limit, you also end up with the fact that the actual limiting factors might be the laws of physics, the resources you cannot do without. That's basically matter, energy, time. And of course, knowledge, as David Deutsch would like to point out. It's easy to do certain things once you know how to do it. Before that, they're absolutely mysterious. Okay, so now I'm going to be running through things. And at this point, I'm going to be kind of glossing over why do I think this, and I would like you to later on ask me questions about that because I'm not just making stuff up. But I would, before doing that, my basic argument for many of these things is this form of exploratory engineering. Let's make a blueprint for something that doesn't exist yet, and I cannot build. But it's a blueprint that we know is likely to work because it fits with known laws of physics, known engineering, known scaling laws. I might take something that already exists and scale it up or scale it down. And if I respect all the scaling laws, I might be able to make a good argument for why that is doable. And that way we can then analyze it, say, okay, that's allowed. That's probably a stupid design. I have many stupid designs. I'm not an engineer. And my argument is rather, if this stupid design can do it, then a better design can do it better. But I'm showing that there is some point out there in the white space that can do this interesting thing. And then there's probably better ways of getting there. So when we start thinking about this, well, where do we end up? We end up actually at first in a very utopian scenario. So how much material wealth can we get? Well, the laws of physics don't really say that there is a limit much on that. Or rather, the limit turns out to be, oops, I dropped my card here. Gravity is a limit. Yeah. So it turns out that the basic limits on material wealth are set by manufacturing. We're living a ridiculously wealthy lives thanks to cheap manufacturing that makes many goods cheap. We can make that manufacture much better. And this is the classic application of exploratory engineering, Eric Drexler's analysis of nanotechnology, which basically shows that this is what you can achieve once you go down to the molecular scale. Maybe we're not going to go down all the way to that, but certainly we see things in biology that also demonstrate that we are ridiculous levels of wealth creation. That in itself is not too surprising, assuming we get enough energy. I think the energy issue is the interesting part here, because given enough energy, you can both recycle material so you get the sustainability part right, and with enough energy, you can also actually clean up your pollution if you have it to a high degree. So can you get a lot of clean energy? And again, it looks very much like, it looks very good actually on the renewable energy area. That doesn't mean that, oh, it's totally trivial. We don't need to worry at all about climate change and energy. It's rather, oh yeah, we need to work very, very, very hard over the next few decades to make this vision work. But there's a very interesting paper by Doyne Farmer at the Institute of New Economic Thinking in Oxford that came out recently that looks at the current trends in various energy production. And typically we get learning curves. The first solar panel was super expensive because it was not very effective, and it took a lot of research to make that. And it was just a small piece. There was no factory making it, etc. The next one gets cheaper, and this is typically true for any product you're making. And this is typically an effect of automation and knowledge acquisition. So it's sometimes called Wrightian learning. The first battleship and a harbor builds is expensive. The next one, now they know how to make it fairly well. It's much less expensive. And then the price goes down. According to a fairly well-defined power law, the rate is different in different industries and for different things. It has been super effective when it comes to making transistors and semiconductors. That's why we have Moore's law for besides some other physical reasons. And Doyne Farmer demonstrated that when you look at the energy system, we get exactly the same thing for solar and wind. Hydroelectric has this problem that there's only a few spots where you can do hydroelectric. There's a limit on the number of rivers you can put dams in. Nuclear is not doing so well in this scenario, which is interesting because it actually seems to be having a bit of negative learning. It seems to be getting a bit more expensive over time. But basically, the big economic model, Farmer and others do demonstrate that, yeah, this looks like, even if you don't care about climate, even if you're a rabid climate denier, you're going to say, yeah, I'm totally going to invest in solar because it's going to save me so much money in the long run. It actually looks like it's a very good economic deal. There's still an interesting set about what kind of solar panels you want to use. Are you going to use the standard silicon ones, or are you going to switch over to perovskites or something smarter based on organic material? I have talked far too much already, so I'm going to skip over my old mainstay of human enhancement, but I'm happy to talk a lot about that. Basically, we have a lot of interesting techniques that look like they're waiting in the wings to enhance our ability, at least somewhat. The problem here is we're talking about something where exploratory engineering has a much harder time saying something solid. It's very easy for me to talk solar panels because here I have laws of physics to lean on. It's much harder to talk about brain-computer interfaces, for example, because here we have imponderables both in terms of biology, what technology we develop, and the legal and economic factors guiding it. But generally, what I found in the working out this chapter about surviving really long on Earth is that, yeah, it looks like you could, in principle, have humanity be totally sustainable indefinitely on Earth. One very silly existence proof is actually use one of those closed ecosystems NASA have been building, a little bit less ostentatious than the Biosphere 2 project in Arizona. But basically you can demonstrate that you can run a solar-powered hydroponic greenhouse that recycles material essentially indefinitely. If you can build that in space, you know you can put it on a parking lot on Earth, and then you can just keep it going. That's a form of agriculture that actually doesn't deplete the soil. You're just recycling stuff. Now, it's an interesting existence proof. It's probably not a good way of actually running agriculture for humanity, but it demonstrates that, yeah, there are ways of doing it. Indeed, soil depletion, etc., is not a given. One of the most interesting things is that we are depleting and destroying a lot of soils and aquifers in some regions, but in others we're actually not doing it. There are actually ways around that. So again, we actually know that it's physically possible to do that. We might want to shift to the sensible way of doing it, of course, which is going to be trickier. But yeah, again, I don't have a time here to talk about other interesting aspects of post-scarcity. I'm going to maybe we can do that in question. There is an important issue about services, and this links over to AI, because most of the discussions about the material world is nice, but most of what we're spending money on these days is actually services. And that is something that can get supplied more cheaply if we get automation that's good, which includes questions about how good artificial intelligence can get at doing it. There are also interesting questions like, what about post-scarcity of happiness, which I definitely don't have the time to go into, and is much harder to put constraints on because we have no idea how to measure happiness. But I think any serious attempt at aiming at post-scarcity should not be content in just making sure everybody had a very good living standard, but also that we're very happy about it. One of the things that shows up when I started thinking about these big long-term projects is also, do I believe this can go on indefinitely? So some of the later projects are ridiculously long range. And then I got this doubt, can any organization actually last that long? So I started reading macro history, and macro historians write really interesting, compelling arguments for why certain things happen, big cycles in history, or why empires must fall, etc. And then I got this doubt, is this true? Do we have evidence? So I started gathering data for survival curves of various big social institutions. And to cut a long story short, the null hypothesis that the risk per unit of time is constant seems to be the most likely one. Normally we have this picture that, the Roman Empire, it got decadent somehow, and that's why it collapsed. It's a very classic story in the Western world. And generally we have this idea that institutions, oh yes, they start up fresh and agile, and then you get more and more bureaucracy, eventually end up with something as stiff as a modern university, and eventually just becomes so fragile that it collapses. But it turns out that the actual data for many different things seems to fit the idea that no, the risk is constant. Even old university like Oxford, 800 years of stupid bureaucracy. The rule book is literally this thick. It's about as thick as my own book. And it's incomprehensible. My book at least have equations you can read. It's still somewhat working. And this works both. The top one, that would be empires. The middle two are... let's see. Now, the top one, then there is civilizations and empires from Wikipedia. And then this one is world systems. That's the closest I have to actual civilizations. And the lower one are European states since the Middle Ages up to the 1800s. I could do the same thing also with corporations, and I get roughly the same thing. There is a weird little tale of super long-lived corporations, but they're usually Japanese hot springs, and they're kind of specialized sources of some very nice thing that people always want. But normal corporations basically have a half-life. So the good news is there doesn't seem to be a built-in decadence in the future. It's not like civilizations must inevitably become too rigid and then crash because of that. The bad news is it looks like kind of, okay, it's bad luck. There is something else that has a constant risk of happening. So actually making sure something lasts very far in the future might require insuring against bad luck. Much harder. But on the other hand, we might want to have backups. Maybe the solution is to have multiple civilizations, and if one of them crashes, the other ones can kind of move in and put up a new civilization where it has crashed. This might be a very good idea, to have multiple planets that naturally are separated from each other. Anyway, this is interesting because it allows us to do a bit of statistical macro history. Let's see, I'm going to skip over the post-humans a bit. Let's talk about them a bit later. But basically, I do think that right now we're rather early in the story. And we're a little bit like the monkeys thinking about, oh, maybe we should turn into intelligent post monkeys. Yes, we're going to get so many bananas. And it's true, we humans are getting way more bananas than our monkey ancestors could imagine. And not only that, we're getting art, science, sport, culture, and we're doing a lot of stuff. And many of these things we would say they're better than bananas. The monkeys would be shocked at this claim and say something has gone wrong. Why are not optimized for bananas? And we can imagine, of course, it's rather likely that post-humans might do the same thing. We might say, oh, if we could make ourselves super intelligent and long-lived, etc., oh, we're going to get so much philosophy and wisdom and science down. And the post-humans saying, yeah, that's kind of cute. We do that too occasionally. We have other things that really matter that you really don't get. So this is the first hint of an interesting problem we have. It might be that the future contains new kinds of value that we should want, but we don't know what it is because we're not advanced enough. It might also be that some of these values might even crowd out some of the things we think are really, really important. And that leads to this interesting question about how much we care for really weird remote futures. But anyway, getting back to the more practical stuff, I love being able to say that and then showing this. Again, we know roughly by an existence proof that's literally orbiting Earth that you can make a habitat that keeps human alive over a span of years. We don't know whether you can do proper food production, mining, recycling, and manufacturing of new space habitats like the International Space Station in space. That has not been demonstrated yet. But I don't think there are that many people say, yeah, that's absolutely physically impossible. I think we have decent technology readiness for many of these things. It's just that over coming decades, it's going to be a fair bit of hard engineering to actually demonstrate it. But I don't think there is anybody who's really doubting that humans could settle the solar system by living on something like the International Space Station, which is not exactly the best place for a baby. And we still need to work out a lot of really interesting questions about how to make it habitable enough. Most of the time when we talk about visions of humanity living in space, we look at these beautiful pictures from the 70s that NASA did for Gerald O'Neill's visions of building these rotating space habitats with large national parks. But of course, the first space station are going to be much more like central Hong Kong or an indoor mall, and that's kind of the best case. I don't know if any of you tried the virtual reality visits to the International Space Station. It's amazing. Every surface in 3 dimensions is covered with clutter. It makes my own desk look totally minimalist. It's a totally messy, claustrophobic environment that the people working there, I admire them, but they have to be rather peculiar people to thrive. But that is probably what you can start out with. That's an existence proof. Then we might want to eventually get to the beautiful stuff. But that is, again, once the learning curves have run quite far. Now, the interesting thing is, if you actually can even use the crappy International Space Station version of settling space, you still have enough resources for having something on the order of a 10 trillion people living in the solar system. That's just assuming we use the asteroid belt. 10 trillion people, that's quite a lot of people. That's also survival for a rather long time, because even if Earth runs into trouble, they're going to survive at least as long as the sun is around a decent luminosity, which is about 5 billion years. That's a lot of future. You might remember my early metaphor there about kind of human lives like fine dust grains. When you start trying to do this metaphor again, it just breaks, because the total amount of future lives in this metaphor ends up being bigger than mountain ranges. So the interesting part here is settling the solar system. I think we have good reason to believe we can do. Not necessarily immediately, not as fast as Elon Musk would like it to do. But I think most people saying, yeah, you can't do it within 1,000 years would have a very hard time giving a good argument for that. Maybe it's not a smart idea to do it too early, but it is definitely feasible. We have that option. Settling the rest of the galaxy might be much harder. So we have the Breakthrough Starshot project, which is an interesting exercise, where we're aiming at using laser propulsion on small solar sails. Strictly speaking, it's not a solar sail if you're pushing it with a laser, but that is intended to reach such a good fraction of light speed that you could reach nearby stars within a few decades. Some very interesting questions here about the material science of those sails, handling microscopic impacts in the dust in interstellar media, and the swarm robotics task of having these stamp-sized microprocessors running with very little power to do something useful once we get to the destination and actually being able to send things back. But this is a serious project and very relatively optimistic about being able to do something in the next few decades. It seems to be relatively on track. It's probably also the most plausible way of relatively rapidly getting to the stars. Generally, the assumption people make in science fiction is that traveling to stars from a literary standpoint needs to be like going on an airplane. You don't spend a sizable fraction of your life in transit. For the story purposes, it needs to be like that. In practice, it seems like the easiest way is, of course, to have a space habitat like that, or nil habitat, and get it moving. It needs to be self-sufficient over a very long period of time. And indeed, it turns out to be kind of tricky. That very long period of time is actually really long. Because if you wanted to move fast, now you have an enormous habitat that you need to push. And the rocket equation is my least favorite equation in all of mechanics. It states basically that you get an exponential fuel requirement increase as the velocity goes up. And once you get to relativistic speeds, things get even nastier. So that multi-generation ship story, while again a good science fiction story, I don't think is particularly plausible. There is a version of it that might be plausible. That is actually if we do settle the outer part of the solar system. So the comet nuclei and other objects in the Kuiper and Oort cloud, they are full of ice and contain a fair bit of carbon compounds. You could relatively easily extract that. And if you have fusion power so you can burn deuterium, then you're set. Solar power doesn't really work that well that far out. But if you actually have deuterium fusion power, then each of these nuclei can sustain a 1 terawatt society for hundreds of thousands of years. That's nice. And after those hundreds of thousands of years, you presumably move to another unused comet nucleus. If you do that and they replicate and thrive, sometimes stars pass by each other. The comet clouds do overlap, and it's actually quite possible to do an island jumping model. It turns out that after 4 billion years, in this case, you have a very slow settlement. At this point, all the stars in the Milky Way have been settled. And also all the deuterium out there has run out. So then people have to, in desperation, go and settle the sunlit inner part of the solar system. The poor future people who have to deal with sunlight again. Now, on the other hand, you might say, well, why not go very fast? So I've been looking more into very fast forms of expansion, what's physically possible. And it seems like sending a biological human very fast, again, the rocket equation more or less makes it pretty absurd. The smaller something is, then it's easier. And it seems like if you have access to nanotechnology or artificial intelligence, then sending a small little sail like that goes off, lands on a little asteroid, build a little base, builds a little bit of solar panel, and build a receiver station, a factory, and whatever you have, it looks pretty doable. In that case, you also actually get not just the ability to send off infrastructure to most nearby stars, you actually get it to setting over intergalactic distances. I have a paper with Stuart Armstrong called Eternity in 6 Hours, where we demonstrate that you can do this across a very vast range. And the total population you end up with, now we need scientific notation, and it's just an unimaginably large number. Okay, so that leads to a fun question. How far can you actually go? And it turns out that we have an upper limit here that's very solid, and that's the acceleration of the universe. Basically, much of the universe we can see but never ever touch. Even if we send a signal at light speed, it's not going to catch up with many of the remote galaxies because of the expansion of the universe. So we get an event horizon, which is about 4.7 gigaparsecs away. We can theoretically get anything inside that if we go fast enough. We cannot get the stuff outside. And the longer we wait, the more stuff, of course, leaves because the expansion accelerates. So if you go slow, many galaxies will run away from you. So this might give you a sense of urgency. We need to get the rocket launch pad quick now. We're losing galaxies left and right. I'm going to get back to this, but it's not super urgent. It might be better to figure out how to make a faster rocket than rushing to the launch pad, because our current rockets are obviously not fast at all. And the slower they are, the smaller the fraction you get is. And if you're going really slowly, maybe somebody stayed at home and built a faster rocket and they're going to be sailing past you. So actually it might be a good idea to wait until you think you're very close to the limit. There are also other interesting issues here about existential risk we're getting to. Another interesting thing is once you start thinking about self-replicating technology and you want a lot of energy, then you get to my favorite tool. This is my version of a Swiss Army knife, the Dyson sphere. So Freeman Dyson, who always pointed out that it should be called a Stapledon sphere because it was actually mentioned in Olaf Stapledon's fantastic science fiction novel, Star Maker. Very worth reading even to this day, although it reads more like an academic paper than a novel. Dyson basically argued that, yeah, where is the logical end point of using more energy? Well, you put up solar collectors around the entire star, and then you get 0.4 Rona watts of power. I got to use the new SI prefix, Rona. I'm very happy that it actually exists now. That's a lot of energy. Now, how would you build it? Again, it seems like many people in science fiction, of course, immediately start talking solid shells. And any of you who've done elementary Newtonian mechanics will smile and say that can't work because the general force between a solid spherical shell and the star in the middle is zero. And I was forced to do that as an exercise in physics. It also turns out that they have a really horrible buckling problem, etc., etc. It's much more easy to just have solar panels that are orbiting the star. And we know this works because we already have a few satellites orbiting the sun getting energy. We already have a tiny, tiny, tiny fraction of a Dyson sphere in the form of a various satellites. Just imagine us keeping up that for a long time, and we end up with a Dyson sphere. Now, the interesting thing is you can do lightweight ones that don't need much material. If you use very thin aluminum foil and use that, the total mass you need is about the asteroid Vesta, which is quite interesting because it's not picking apart entire planets, which Stuart Armstrong and me did in our paper about settling the universe. We kind of looked into disassembling Mercury, which is the environmental impact statement is going to be kind of messy. There might be an environmental impact statement of building a Dyson sphere too. You might actually want to think carefully about the reflections and the heat emission hitting Earth, because you might presumably not want to mess up Earth here. It also has these interesting properties that, yeah, you get a lot of surface area, which also means it's a very interesting antenna. If you think of it as a phased array antenna, you can do some amazing things, especially since you have a lot of power to play around with. It's fairly bad as a weapon, which I'm happy to say. For various reasons. One of the reasons is, yes, you can send an enormous amount of energy at anything several light years away, but if that target has moved in the intervening years, you miss them. So it's not very good. You can use it to reflect starlight to really gradually push stars. I'm going to use that in a few slides over. As I mentioned, you can use this to send off spacecraft with lasers really fast. Basically, the reason it's so interesting is that you get a lot of power. We understand fairly well how you could go about building it. It also couples to the electromagnetic field in a lot of interesting ways. And this is something that is probably going to look very much like a steam-powered spacecraft, some Victorian inventor envisioned, by the point where we can actually get to it. I expect most of my kind of analysis here to turn out to be mildly ridiculous, but it kind of shows that, yeah, this is allowed by the laws of physics. It also has interesting issues about, of course, looking for aliens, which was why Dyson suggested in the first place. Let's look at weird infrared objects because that might be advanced civilizations that have built their Dyson spheres. So we've been looking around and we haven't noticed anybody doing a Dyson sphere yet. Other interesting things that is, of course, how long would you survive? And again, if we get our act together and don't kill ourselves, which is maybe a big if, but kind of worthwhile to work on, it seems like if we survive like a mammalian species, we still have about 1 million years. That's kind of really long. If we don't crash our civilization, that means that we're going to have 1 million years of history, art, television, computer games. That's a tremendous amount of value, and sometimes disvalue. But that is, of course, assuming we're just behaving like any other mammalian species. Actually, we are probably way more adaptive because we do exist in a lot of different ecological niches. On one hand, we have now created a somewhat fragile ecological niche for ourselves because we're dependent on a global, complicated, interconnected supply chain that can sometimes crash for weird reasons. But we also have a lot of ingenuity technologies and even slack in the form of stored resources. And if we actually get good at avoiding existential risk, it also looks likely that we can avoid even mass extinction level risks. Many of the things that were really bad for Earth's biosphere in the past, I think we have some inklings about dealing with it. Maybe we can't stop a supervolcanic eruption like the Siberian traps, but I'm working on a paper on volcano engineering. So maybe give us a few 100,000 years and maybe we have an idea. If we actually do that, then the natural time limit is how long the Earth's biosphere lasts, which is about 1 billion years, give or take. It depends a little bit on annoying issues about the sun getting brighter and the ecological responses that people are having a hard time modeling. But it's pretty clear that eventually you get a problem that we run out of carbon dioxide and photosynthesis becomes infeasible, the biosphere crashes, that's bad. Also, if you put up a solar shield, you can probably add about 1 billion years at the very least. So I have an ethics paper where, together with Karim Jabari, I analyze a little bit about technical stuff, but most of the ethics about wouldn't that be actually a very good idea to do? Even if you are an ecocentric ethicist, you don't care about humans at all, or maybe humans are even a bit negative, you might still say, oh, those ecosystems, if they can keep on going, we might actually allow humans to be around if they put up that solar shield. Now, that is still just 1 billion years. If you settle the solar system, as I mentioned, we might get 5 billion years. If you settle the Milky Way and just use solar power mostly, then you end up with a lifespan for us on the order of as long as there are stars, which is about 10 trillion years, 10 to 100 trillion years. Eventually, the stars go out. But there are other energy sources. I spend far too much time working out nuclear power, black hole power plants. Nuclear power doesn't really have a future once the stars go out. You don't get new isotopes. Fusion is kind of problematic once you have fused everything. But then you can take that mass and drop it into a black hole. Black hole accretion disk can actually reach an efficiency up to 42% of converting matter to energy. That is a lot. That is actually much more than you can get from the stars themselves. So in many ways, the fact that the stars are kind of wasting a little bit of a mass right now by fusing it and turning it into starlight, which is still heavier. The total amount of starlight in the universe compared to the total amount of planets, but by mass, there is actually more mass right now in starlight than in the planets. So light is heavier than worlds, which I think is one beautiful poetic fact about the universe. But it turns out that black hole power, that would probably last us throughout the degenerate era after the stars run out. Eventually, we have this fundamental problem that we might run into proton decay. And that, of course, allows us to do a ridiculous amount of computation. The basic problem here is that computations that erase information have a thermodynamic cost. Every time I erase a bit, Maxwell's demon shows up and says, "Pay up, sir." I need to pay a little bit because I have when I turn a bit into a zero, I reduce the entropy of the universe. That entropy needs to go somewhere. Now, if I'm clever, I can do various clever accounting and do reversible computation, and then Maxwell's demon doesn't have to be paid. But usually that is rather slow. But on the other hand, it might also be a useful way of making computers run with much less heat emission, which is great when you wait until the late eras. And quantum computing is also natural reversible. We're still not quite there yet, but it looks like you can get even more computation. What would we use these computations for? Well, that's the problem. We don't know what advanced civilizations want to do. Maybe they're playing World of Warcraft. Maybe they're doing flame wars on social media. Maybe they're running ancestor simulations. I can't say anything useful about that. I can just look at these outer limits, and they are interesting because they tell us some things that can and cannot be done. For example, the size of ancestor simulations are somewhat bounded by the computation. There are some forms of high resolution simulation of the past that you probably can't do with these resources, which is interesting if you're philosophically inclined and wonder, is this real or is this some future simulation of the present? It seems like I already mentioned that thing about black holes. And I'm running out of time because I want to hear your questions, but that thing I mentioned earlier about pushing stars using reflected light, turns out that you can do this step-by-step analysis that if you use mirrors to reflect starlight, you get the wimpiest rocket you have ever seen. But over a span of about 4 or 5 million years, a typical star can be, its trajectory can be changed enough that you can engineer a two-body encounter with another star. Now you get the gravitational assist, and suddenly you get a change in velocity that's on the order of 10 kilometers per second. And you can use that, of course, to guide them towards other stars. So basically, you're playing the ultimate form of billiards here. And there is a lot of cool stuff you can do, especially once you get into free body encounters. The free body problem allows you to basically use binary stars as energy storage. You can use a star that has a bit too much energy and put it into a wider orbit, or you can tap it to give it velocity, or you can store it in a parking orbit for a little while, and because you're waiting for some other stars to arrive. What would you use this for? Well, one way is to actually turn a galaxy into a kind of literal, very stupid rocket by just throwing stars out in one direction to accelerate the galaxy in one direction. I calculated that you could make the Milky Way move 50 kilometers per second this way. This is probably one of the most stupid projects I suggested, because it's probably the stars we care about, not the dark matter and all the other stuff. But you could also use this to send the stars over to another galaxy where you carefully capture it. And indeed, when the Andromeda galaxy and the Milky Way start merging, we might want to manage that. So instead of having this all turn into this big elliptical galactic mess where that blows away all the gas, so no new stars can form, instead you carefully align things and you kind of capture all the stars into binaries, so you actually keep all that energy but to use in the future and actually maintain a healthy stellar ecosystem. Now, this is getting to the kind of fun questions about our cosmic insignificance. So generally, life is a kind of phase transition of matter. It's a really weird one because it's a reorganization of matter, but we have a different set of cosmological size scales. So if we think about the cosmic web, beyond a certain point, it's fairly homogeneous, at least it's believed. There is some argument about whether it's some larger fractal structure, but basically it looks like beyond the 200 megaparsec scale, it's basically homogeneous. Now, we could reorganize galaxies and stars on the order of about 50 megaparsec. For example, to stop the expansion of the universe, at least locally, we could send all the stars and galaxies back together. So we could take out little chunks and make our own little stable universes so we don't run out of resources, or we might want to have a big civilization. That creates a nice size scale. But it seems like we could also expand much further, like I described earlier. This wouldn't be enough to reorganize all the matter in there. There is not time for that, but you can make a lot of these smaller chunks inside. And this sets a scale of organization in the universe that's actually larger than the end of greatness scale astrophysicists have described. It might be that if this scenario is true, when you want to describe the structure of the universe on the large scale in the relatively far future, leaving out intelligence and life would be a serious error. And this is, of course, my response to Guy Cahane's quote. He is a colleague in Oxford, and he's very fun and very snarky, and he wrote this paper about our cosmic insignificance. And he even has this line that, are we supposed to be doing these grand things to be significant? And his answer is, you're significant if a description of a system you're in that leaves you out is going to be a bad description. If I want to describe what's on this desk, if I leave out that computer, it's kind of a failed description of what's on the surface of this desk. If we talk about this room and leave out the fact that there are people in the room, that also kind of fails at it. On the other hand, there are probably some dust grains somewhere in the carpet that if I forget to describe them, we still have a kind of good working description of how this room works. Now, if this argument works, it might be that long-run intelligence, not just us, but other intelligent species, might be quite significant for cosmological structure. We're making ourselves significant. There is still a scale between these vast bubbles that are set by the probability of life and intelligence emerging, which we don't know much about. That might be a very low probability, so it might be a very large scale. That might be even vaster than the scales I'm talking about. But yeah, it seems like there might actually be a really important role for intelligent life acting here, given what we know about physics right now. And the coolest thing about this phase transition is that this depends on what we choose to make it. If we think that we should maximize happiness, maybe we're filling those bubbles with happy minds. Maybe it's complexity. Maybe it's justice. Maybe it's a mixture of all of these things. But we can't describe that in terms of the laws of physics. That has to come down to what the individual civilizations and maybe even members of the civilizations choose. Okay, I'm running out of time, but let's just mention that we could be wrong about a lot of stuff. There's a lot of very fun ways of exploring what happens in these scenarios if you allow things like fast and light transport or time travel. What if we're totally wrong about quantum mechanics, etc. The really interesting thing for me is, okay, we know a fair bit about how the universe works, but we might not know what it should work like. So we might actually have important forms of uncertainty. So one thing is, of course, maximizing local utility. This might be something like turning matter into computers running very happy minds. If happiness is the highest value, we should be paving the universe with these happy little computers, and that's the best thing we can ever do. Of course, from the outside, that might just look like somebody converting it to paper clips, but the happiness thing looks, it might look similar, but it's much better. One interesting thing about that is it does. That happy mind and that happy mind might not actually need to talk to each other. So the fact that they are disconnected because we're in different galaxies expanding apart at a very fast pace doesn't matter at all. So you might just want to go out as far as you can and create happy minds. But you could also have ideas that there are computations that needs to be done. So maybe the number of operations. In that case, you might actually want to wait until the universe cools down, because you can do more computation at low temperature than at high temperature. And now it's sweltering 3 degrees above absolute zero. So this is kind of a bit too hot to do serious work. But if you wait a few trillion years, it cools down considerably. And then you actually reach an asymptotic temperature set by the acceleration of the universe, at which point you might then start harvesting this. So in that case, you expand first, and then you wait and sleep in until it's cold enough, and then it's kind of harvest time, and then you do your computations in the far future. Of course, there you have an interesting problem. There might be some people or beings around in the meantime making use of those resources for other stuff. There might be an interesting moral trade issue here where some people might say, I actually want to mess around with the universe now in the springtime with all these beautiful stars and nebulas. You, the computer nerds, you can wait a few trillion years. We're not going to waste any matter. You can run that in your black hole power plants, but we want to play around now. If we could actually make a deal that both sides could trust, this you could totally make a good moral trade here. But it might also be that actually it matters to be causally connected. We are hopefully going to have a nice conversation because we're causally connected. Right now, it's kind of a one-way thing. I'm sending you signals and you're not able to respond very much. Similarly, in the expansion of the universe, you might end up with these disconnected clusters where whenever somebody comes up with something great, they can't tell others. It might be the true value resides in this ongoing discourse, whether that is thinking deep thought or just the everyday stuff of civilization, love affairs, and all of that. In that case, you want to expand a bit, but not too much, because then you drift apart. So you get a much more limited expansion. Then, of course, you might want a different strategy if you want to survive really long time. And then there are the people who actually say, oh, all of this leaves me very, very cold. I don't need to move galaxies. Guy Kahim was totally right. That's kind of silly. I don't want to leave Earth. I want to live in a nice little village where people are playing cricket. I can have a cup of tea with the local vicar, and I have normal friendship with normal people. None of those weird post-human cyborgs. And I think this is quite possibly a totally valid view. It might be that I'm utterly, utterly wrong. And indeed, most people would probably want to ensure that they get the sustainable utopia like that. It might be, of course, again, that we can do a moral hedge here. Yep, Earth, we turn it to the nature preserve, and people are playing cricket there, and the rest of the universe, we're doing other things. There might be interesting philosophical problems here, because sometimes you get nosy values. It's not enough that I get to do this. You should also not want certain things that I think are evil or bad to want. So there are some philosophies that make very bad neighbors. But the cool thing is, many of these scenarios, they end up having moral traits. You can actually do business. If I think vegetarianism is the most important thing and you think poverty reduction is the most important thing, we might make a deal that you go vegetarian and I donate extra money to poverty. We're both better off here. and the world is likely better off. Figuring out how to do this well might still require a bit of thinking. And I think there's an interesting philosophical issue as well as a practical legal issue. There's also actually an astronomy issue. I have friends in the astronomy world that are curious to look for different forms of expansion in the universe. If we see an alien civilization, can we see from the way it's expanding or not expanding what kind of set here they belong to? So you might also have heard about the astronomical waste argument. We seem to be very early in the history of the universe, and the total future value is really literally astronomical. So if we wait, we're losing galaxies. So maybe we should run into the rockets. But actually, if we go extinct before that, because we're destroying ourselves with nuclear rockets that are unwisely put together or doing some other things very badly right now, then most or all of the future value is lost. So actually, this argument seems to imply that it's more important to reduce existential risk. And this is where we're getting back from my kind of far-flung cosmological stuff to questions, what are we actually going to do next Tuesday? Because it seems like many of these grand future schemes do imply things about the present. Many of them are of the form, more research is needed. But this argument is interesting because it suggests that if we care about this vast future happening, we might have to make sure, since we're very early, that we don't increase risk too much. And there is a weird irony here that being super optimistic about the future actually makes you very cautious in the near term. I'm an old transhumanist. We were in the 90s. We wanted to have a singularity as soon as possible, and then we started realizing, oh, AI safety is a thing. Oh, having the singularity as quickly as possible might be a stupid idea if you can't make a safe, survivable singularity. Maybe we should try to do that faster than the singularity. Another interesting thing that happens in this argument is that I'm talking about very time-rich future. It's cheap to get extra time. If we knew the universe would end in 100 years, we would need to hurry up to do good stuff over the remaining 100 years, and we would get a very different strategy. But delaying things is, at least in the large scale, a good thing. Now, individually, of course, we might want to have life extension, have good lives, and do things that are good for us or the present generation. But if you're taking a time-neutral perspective, having a very long future means that you can actually put off doing a lot of things rather far into the future. And I think, in general, you get interesting ideas. Like Will MacAskill pointed out that maybe we need to avoid making super big mistakes rather early here. So we might actually want to, once we fixed some of the very urgent needs we need to fix, we actually need to spend a fair bit of effort to coordinate so we don't make a mess of things. This involves things like suffering risks. When I'm talking about spreading life to all the planets in the universe that can have life, some of my friends cringe because they think that wild animal suffering matters. It's not just the suffering we humans inflict on in factory farming that matters, but also the fact that a lot of animals out there in the forest are not having great lives. They're suffering, and maybe that suffering counts for something. Now we have one planet with suffering animals. If I get to put up 10 to the 20 new planets, I might have increased the total amount of suffering in the universe tremendously, and maybe not increased the value as much. Personally, I disagree. I put them kind of on the same scale. I'm fine with that. But I'm willing to agree that I'm not the greatest philosopher ever. Maybe they have a point. And we better figure that one out before we put in a lot of life on the other planets. And there might be other things we need to coordinate about. Indeed, I've been using the exploratory engineering approach to kind of trying to figure out what it would be good to coordinate about. And there's a lot of coordination needs we might want to aim at here. In some cases, it's just practical stuff like exchanging crypto keys so we can talk to each other. There's some very fun things you can do by exchanging quantum entangled pairs. So you coordinate even if you can't talk to other people. But many of them are also setting up useful ground rules so we don't mess up the universe too much. So where do we end up with this grand futures thinking? Well, the future is big. It looks like we have very good reasons for why it could be very good. And that means that we want to preserve that option value. There are also a lot of things we don't know. So we might not want to avoid reducing our options too much. We probably also need this coordination. Right now, it's not too hard because all humans are within 1/7 of a second as the electron or photon flies in communication. maybe in a few decades, we're going to have some people a few minutes away. That's already going to reduce the coordination ability a bit. Once you're getting out of a solar system, it's actually going to be very hard to coordinate. So we probably want to figure out better forms of coordination. And it's worth noticing also that we're doing that continually. A few centuries back, it would have been absurd to have something like the United Nations. The United Nations, for all its fault, is an attempt at coordinating humanity as a whole. It's very limited and not exactly fit for purpose, but it's orders of magnitude better than what you had a few centuries ago. And in a few centuries, we might have something even better. We might want to work on better tools for coordination, which doesn't necessarily have to be like the United Nations. And it's also interesting to think about what ways can we affect these futures. And part of it is when you shape a technology, you quite often shape its usage by the assumptions going in. The personal computer was invented by California libertarians who felt like we need to democratize the computer. Everybody should have access to computing power. It should not just be locked up in mainframes handed by people in white lab coats. It's going to be a force for deliberation, liberation, and creativity. And yep, it didn't always play out as they wanted to, but they put in a certain agenda, certain assumption. The same agendas that you find in shaping internet. You can even find interesting agendas in setting standards, and standards and laws remain with us for a very long time. So we might want to think about the renegotiation over the next few years about the space treaties and how to handle space. How do we do that right? When we think about climate change, what things are we putting into the rule book that is going to be around in decades and shape not just climate but other things? For example, some of the biodiversity conventions were intended to help safeguard biodiversity but have interesting effects on the biosciences and biotechnology. That was a bit accidental, but we might want to coordinate here. And then, of course, a lot of the stuff I talked about here might not happen at all. I think not because it cannot happen, but because we do not want to do, or other things intervene, or we find more important possibilities. And generally, one of the coolest things about being an intelligent creature is that you can make ridiculously unlikely things happen because you can plan. Our ability to set things in motion is astonishing. I can press a key on my computer, and that sends signals across the world that make stuff manufacture and then arrive at my door. This is an amazing level of coordination. It involves having pieces of matter do stuff they normally don't do. Normally, you don't find semiconductors doing anything in nature. We have arranged silicon atoms and a few dopant atoms to do interesting things. We have arranged systems of information that generate complicated economic transactions, and a printer somewhere printing a T-shirt with a logo stole by downloading it from somebody's website. And then there is a logistics system that have somebody deliver my tacky T-shirt to me. It might not be the most impressive demonstration of intelligence that I could print out my own T-shirt, but that is a demonstration that intelligence can make something utterly unlikely happen, because normally in nature that doesn't happen. T-shirts don't just pop up. T-shirts literally don't grow on trees, but we could in theory make that happen. And that is of course also why predicting the future is pretty hopeless, but we can look at the constraints and boundary conditions and use that to think about what are good futures, bad futures, what are options, and then try to guide things. And also of course I'm very much into having a positive vision for the future. Recently at an AI ethics conference, somebody pointed out that we are problematizing things too much. Nobody at this conference has ever raised anything positive without somebody immediately saying, but, and then bringing up that there's a problem with justice or resources or power or whatever. And our immediate response in the panel was, but, and we wanted to problematize it. And then we realized, oh, and it's kind of true. We are very good at problematizing things, and figuring out what could possibly go wrong is valuable. But we also quite often, especially in academia, use this to inhibit doing stuff. We should be using it as a guide of, let's not do the stupid things, let's learn the lessons. But far too often, I think we have, as a civilization now, gotten into the idea that we can always see downsides of everything. It's not hard. I think you have already found 1,000 downsides of stuff I've been bringing up here. It's not hard. The real interesting thing is, of course, we still want to have upsides. We still want to make that. And I think that is where we want the existential hope. That is where we actually need to have the grand vision that, oh, the future could be as awesome as our world actually is awesome compared to how it was in the Stone Age, which was infinitely much better than it was in the gaseous plasma a few billion years ago. I think the universe might very well, in a few billion years, be so fantastic, awesome that we can't possibly imagine it. And we get a chance to actually help that happen. Thank you.
Great. I'll let you take a sip of water. And in the meantime, just gonna quickly announce, we're gonna do a audience Q&A now. I'm gonna pass the mic around and you guys can ask questions. And afterwards, we're gonna have a little apero here. Two of the EA community members are just buying some snacks and drinks, and we're gonna have an apero here. So you're all invited to stick around for that. Okay, I'll start with the mics now. Please raise your hand if you wanna ask a question, and then I'll come to you. Okay, you wanna go?
Yeah.
Sorry.
So a very nice talk. I want to ask you, like, why do you worry about the long-term future after all we all died in the short term?
Well, even if I'm not around, I might still have preferences about the future. When people built cathedrals in the Middle Ages, many of them knew that we are not even going to live to see this cathedral finished, but it's an important project. It's good for our community. And you can take a totally non-personal affective view and say, oh, we're happy minds in the future. I don't care about who they are, but I might want to have a lot of these happy minds. And well, I'm also a transhumanist. I'm signed up for cryonics. So if I'm dying, please freeze me in liquid nitrogen and try to revive me once the technology is there. I'm also hoping that life extension might allow me to be around. So I'm selfishly hoping that I'm very lucky and get to see a lot of this. But even if I am not lucky, I think we do care about the future. Samuel Scheffler had an interesting book about care. Why do we care for future generations? He had made this thought experiment. Imagine that 10 years after you die, then the universe disappears. Versus a scenario where 10 years after you die, the universe keeps on going. Which one would you choose? And the obvious answer practically everybody says is, of course, I want the universe to continue, even though there is no value for them. And the real thing that is going on is most of us have this implicit assumption that we're connected in a bigger whole, that it's actually a good thing that humanity or our family or our lineage or tradition or ideas continue. Now, this can be motivated in a lot of very different philosophical ways, but I do think that we actually do generally want the future to be awesome. Thank you.
Could you please elaborate a bit on the notion that life is a transition phase of matter?
Yeah. So this is not my idea. I stole it from, I think, Freeman Dyson, because he's usually first with these kind of things, but I've seen different versions of it. So normally when we think about phase transitions, it's the organization of some material that changes. It's basically its conformation or the information inherent in it. So life is, of course, in some sense, a form of soft matter, at least terrestrial life. And it's an interesting organization because you get these open systems, energy is flowing through them, maintaining a low entropy state. It's self-building and self-replicating. But the component atoms, of course, normally out in the environment, they don't do that. And you can imagine if we generalize the concept of life a bit, so we include our machines and our technosphere, we could say that this is a form of organization of matter that picks up energy in the environment and uses it to reorganize inert matter into itself, expels waste energy and sometimes waste matter, and can spread. Now, the interesting part here is the self-replication, because self-replication, again, it's a thermodynamically reversible process. If I have some structure that replicates, it takes matter and turns it into a copy of itself, there are some interesting thermodynamic limits. There are also interesting limits on the quantum level. There is actually a small possible self-replicator because the no-cloning theorem in quantum mechanics forbids perfect self-replication on the quantum level. So there is a lot of interesting links here to the laws of physics on what the simplest life could possibly be. But the cool part here is that what kind of matter can turn into life? Right now on Earth, we only know that, okay, it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and about the 10 to 20 other atoms that are involved. And generally, using bacteria, we can turn almost the pure elements into this form of organization. In practice, of course, it's mostly happening using normal molecules. We might generalize this because some forms of life, us, could actually build machines to convert elements into our kind of elements, or maybe make machines that we might add to the definition of life. Maybe if we have robots out in space, we would say those robot rovers on Mars, they're kind of now honorary members of the living kingdom, and they're adding aluminium and the silicon to their role. Now, it's an interesting phase transition because it doesn't seem to be a proper first or second order transition. So maybe I'm stretching the statistical mechanic definition of phase transition a little bit too much here. But it is a reorganization of matter into a particular pattern that seems to be able to spread, at least under some circumstances, and stable under a lot of circumstances. In some kind of vast phase diagram of the universe, obviously there are temperature limits. Beyond a certain temperature, I don't think you can have life. I'm not certain whether that is some thousands of Kelvin because molecular matter melts, or maybe you can have nuclear matter life so that can go further up. But there is probably some upper temperature. It's not obvious either where the lower temperature limit is. It might be that you could actually have silicon circuits and the robots working at near absolute zero. Similarly, pressure, very unclear, but you can kind of argue that under some circumstances you can get this phenomenon. And it's interesting because matter where life has not shown up is just sitting there being matter and doing the normal matter stuff. But once you introduce a bacterium into a nutrient medium, you get this exponential growth, and that totally changes even the behavior of a nutrient medium. It becomes a thick bacterial sludge. If a bacteria motile, it even generates weird collective behaviors of motion, which are very funky. So I think there is something interesting one can do here, try to analyze what kinds of phase transitions are possible. And this matters not just in the sense of talking about what is the physics of life and the physics of the universe. It also gets to interesting questions. I have a big appendix in my book project about conflict. Is offense or defense the most powerful force on different scales? That says a lot of things about how scared you should be about aliens or internal conflicts. And a lot of it depends basically on how easy is it to disrupt organization at a distance. What resources do I need to use to destroy something over there? And honestly, I don't have a complete theory there. There seems to be a very cool information energy trade-off. If I have a lot of information about how to mess with that object, I can just use a tiny amount of energy to interfere with it. If I don't have much information, I need to throw a bomb at it instead. The interesting thing is that, again, ties it into physics. We can actually analyze a bit on the physics of conflict and say at least some rough things about how safe the universe looks. The good news is on the very vast scale, the universe looks very safe. It might be a bit unsafe on smaller scales, and it seems to be a non-monotonic function, which is very interesting, but it's early days in this research. Yeah.
Great talk. Thank you very much.
Thank you.
I know you talk about like the life expectancy of different civilizations. With our world today, would you consider us one civilization or separate civilizations still? And how do you see that evolving?
Yeah, so defining civilization is also one of those tricky things. I have some people from the social science who immediately cringe when I say civilization because they know that, oh, no, now that white male colonialist is going to be talking. Civilization is a dirty word. But actually, I use it as a general idea for a structure across time and space, organizing a lot of people for long-term projects. So in that more neutral sense, I would actually argue that, yes, we have one global civilization. It's split into a bunch of different nation states and other organizations that are sometimes at each other's throat. But it's still actually rather deeply connected with a lot of things. So there have been these attempts of defining civilization tighter. So you can sometimes say empires or civilizations. So the data I was showing earlier, one of it came from Tagapera, who's done a marvelous job of very carefully defined political organizations. So they're basically the biggest political organizations, and he's been mapping how they expand and disappear, and so you get the spatial temporal dynamics. But many of these empires were, of course, part of bigger systems. So there is something called world systems theory that is arguing that in many cases you have maybe a central power and various powers around them, and they're all talking among themselves. And then there is some barbarians outside that they don't care about. And some of the barbarians want to get in, so they actually think they're part of a system. But further away, nobody has ever heard about this place. Those systems, there might be just a handful of them, maybe 10 and 12 of them. But then you have this argument that actually that clock that has 12 hours divided into 60 minutes, and that is because the Babylonians did it. And they are actually drawing on a few Sumerian ideas. You can kind of argue that the Sumerian civilization got subsumed by the Babylonian civilization, and then it interacted with the Greeks and Egyptians, and they kind of merged together because of Alexander the Great. And then came the Romans, and so on and so. We have gradually merged together a lot of local civilization into this global civilization. And by that standard, it's been doing rather well. It's been around for 5,000 years. And even if we flub it right now, if we don't go extinct too or crash civilization too badly, that super civilization is still likely to go for a very long time. So a lot of it might depend on the scale you're using. So often in space terms, especially when thinking about aliens, we talk about alien civilizations. They might be divided into all sorts of political powers and whatnot, but we might just say from our distance, they look like one blob. And maybe that is what our civilization is like. It's one blob. Sumerians and Chinese and modern Westerners, yeah, they're the same. Yeah, those cyborg post-humans of the 50th century, yeah, they're also similar to Sumerians.
We're going to take 2 more questions.
Hello, thanks. Yeah, I think I was trying to think like, what am I actually like, taking home? And I've seen like a lot of more like, I think like morality is kind of a key corner of like actually deciding of what to do, right? Like one can see a lot of projections and physical limits, but if you ask like, what shall we do about it? It's actually like how we think about morality. And then you presented several views, and then you named it, okay, you're self-transhumanist. If I was asked like how we are to proceed, I would say like probably like one should use evolutionary approach, and like whichever is the fittest will survive. But the question here is, do you see the convergence of different moral approaches, or you would also agree that the fittest will survive in terms of which morality will?
So this is a really interesting question. Are we going to converge to the one true morality, or is it just that we're going to invent more and more? Maybe relativism is actually true, and we just get different societies going off in all sorts of directions. I honestly don't know. I might work in the philosophy department, but that doesn't mean I know what true morality is. I heard a little bit too many people who are absolutely convinced about stuff, although most good ethicists are not very certain at all. They're very deep meta-ethical questions we don't know. And indeed, some of my friends have been trying to make a bet actually about, by the point we have expanded so far that different branches of humanity are no longer in causal contact, will we have reached some kind of agreed on view of morality, which might still be that there are 17 self-consistent moral systems, and there is no particular good argument why you need to choose one over the other, but they are known to be self-consistent. Or is it that people are still coming up with entirely new moral systems, a way of handling it? So we don't know. And for me, that is kind of fine. I think we can have an open-ended view on this. We probably don't want to foreclose a lot of possibilities. We need to be pluralist because we know we don't know. That doesn't mean, of course, anything goes. There are a lot of behaviors that are really destructive and bad. And I think in many cases we can say, yeah, in theory, it might be the best thing ever to torture little children, but now we're not going to accept that. We can actually set up things. Maybe if we find out in 1,000 years that we were wrong, we're going to reinstitute that behavior. But there are ways of not just letting anything go, but you might still want to keep things open-ended and pluralistic. That means that we need to work quite a bit of figuring out better ways of moral hedging and ways of actually having different systems work in parallel. So I'm totally fine with people being Amish and not using high tech if I get to have my cyborg body. I'm not happy if they want to prevent me from being a cyborg. And I think we can figure out ways of doing that. And to some extent, we've done that with some political philosophy. We have come up with ways of imperfectly solving it in many societies. There's still a lot of limitations and boundaries on how different your morality can be and still function in a big modern society. But we have some tools, and I think we can make better such tools. So this is actually a research area that I think is quite valuable. There was the final question somewhere.
Final question, we'll try with the quick one.
So it seems now like to me that we're accelerating, well, the innovation in technology is accelerating faster than like our evolutionary speed, in that like our brains can't really keep up. Like we use cell phones are almost like an internet, like an extension of ourselves, because there's just so much information, more than what we're used to. And at the same time, like it seems innovation is always trying to replace more and more high level human intervention. So my question is, would we get to a point where our destiny would be to hand over to digital descendants? Like we don't go extinct as a species, but we live through them, in that if we didn't exist, then neither would they, but humans as a biological species.
Yeah,
wouldn't
yeah.
exist.
That's entirely possible. Actually, on the way here, I was writing a little essay for the conversation that was about what a world where we have left stuff over to digital people would be like. Now, it's not entirely clear that it has to be like that. But I think it's pretty likely that there are advantages in being software that you can't get by being physical. Just as being physical gives you certain advantages that software doesn't have. The software on this computer is utterly dependent on getting electricity, and it's not self-contained. The software can't exist outside a particular computational matrix. We are somewhat self-contained organisms. We can survive in surprisingly diverse environments, not out in space and not in the bottom of the ocean, but still a large number of environments. That self-containedness comes at a price. We're slow, we're inefficient, we have a lot of redundancy, but we also get a lot of robustness. Different modes of existing have different advantages. And I think my preferred future is where you just get a lot of modes of existence. I think many of them have very nice virtues of their own. So I rather have it, maybe the entities in charge are in one category, but as long as you have a good cooperative sphere between them, even the entities that are not in charge might still say, yeah, very legitimate authorities here. They actually know how to move stellar clusters, but we are sipping tea and having cricket in a way that they cannot possibly do, and that's kind of fine. And they are saying, yeah, please have your tea and cricket. You're a very good backup if something goes wrong. Oh, if you only knew the problems we have to deal with among the Jupiter brains over here. Oh, yes, please play cricket. Thank you.
Okay, thanks everyone for coming. We're gonna have a little apéro here. You're all invited, so please, if you still have time, stick around, ask some more questions, and socialize with the other EA community members. Thank you.
Thank you.